This is our second video with the formulas. And this time we will apply these formulas to a specific case when the acceleration does not depend on time. I will write both components of acceleration as constant. They do not depend on time. Ax is constant, and I will call it Ax, A sub x, c, to emphasize that it does not depend on time. Ay will be also constant, does not depend on time, and this is Ayc. So it's very useful example. So for example, trains are moving with acceleration that is constant, or your car is moving with constant acceleration, or objects fall with constant acceleration. We did it already for one-dimensional motion. Let's do it real quick for two-dimensional motion. So I want to find, and you see I use different color, and these formulas will be in a separate box because we can apply them only for the case when acceleration does not depend on time. So what is Vx in this case as a function of time when I have Ax constant? Integral Ax, if I skip x, that would be a horrible mistake because this is x component of acceleration. Axc dt, and this is constant. I take it out of integral Axc times t with arbitrary constant c, and I need to find this arbitrary constant from the initial conditions. Something has to be given. So let's assume that my velocity, x component of velocity at time moment 0 was v naught x. I have to add x, we don't forget about it. So if that was the case, then what do we have? I keep going, Vx at time moment 0. Time moment 0, this guy is 0. What is left is c, and this is equal to v naught x. So what is my x component of velocity when acceleration is constant? It is Axc times t plus v naught x. So in case when we have constant acceleration, we can immediately write the velocity. This can find our velocity using this formula. This is a shortcut for us. Now I can do the same for Vy component of velocity. I will use formula 6. I'll do the same integration, and the result will be Vy as a function of time will be Ayct plus v naught y, where v naught y is a number, it's initial velocity, y component of initial velocity. So now we know how to find both components of velocity when we have constant acceleration. Last thing that we need to do, we need to find the position. Again, look, I'm writing in blue, so those formula you can apply only for this specific case when acceleration is constant. The last two formulas that we need to write are for the position, x and y component of the position. So what will be x component of the position? Well, I will use this formula, formula 7. I will integrate v sub x. Integral Vx of t is this, Axc t, right here, plus v naught x, plus v naught x dt. And we integrate, AC is constant, Axc t squared over 2. Can you see 2? Yeah. Good. Plus v naught x, constant, times t, that's integration, and plus arbitrary constant that I need to find to satisfy my initial conditions. I will call initial position as x naught. So x at time moment 0 is x naught. And we need to do the same thing for y component of the position. I use formula 8. I do the same procedure just now using Vy component of the velocity. And what is the final result? I will write it here. If you don't see it, scream. I hope you will be able to see it. Y is a function of time. Y y component of acceleration, it's constant, t squared over 2. This is this guy, plus v naught, now it is y. If I skip y, it will be horrible mistake, don't do that. Plus position at time moment 0, I will call it y naught. And look at that. We know how to find the velocity. If we are given x component of acceleration, we know how to find x component of the velocity if acceleration is constant. I will call it formula 9. 9. Y component, 10. 11 for the position, and 12 for y component of the position. X component of position, y component of position. So that was our second video on two-dimensional motion. We wrote formulas for the case when the acceleration is constant. Again, I hope that you will have all these formulas in front of you when we start solving the problems.